Hello everyone. Today's topic is instrumentational amplifier using 3 op amps and also advantages of 3 op amp instrumentation amplifier. So in previous class we are already discussed about analog signal means continuous signal have infinite number of levels and high noise, the amplitude high, the limitation of noise purpose we can limit the amplitude. So amplitude limit is the biggest problem, or we can get the distorted output. Then we go for digital is nothing but contains discrete signal and it have only the levels of 0 and 1, that is nothing but binary 1 indicating high position and binary 0 indicating low position. The digital signals are more accurate than analog signal and less noise compared with analog signal. Costly digital signals are high cost compared with analog signal. Next, digital signals it occupies more bandwidth and analog signals it occupies less bandwidth. Next, instrumentational amplifier. So it will be designed by using of 3 op amps. The 3 op amps, one will be working as buffer amplifier and it contains 3 inputs. The third input is called V reference input. Instrumentational amplifier, it can use as buffer. It uses for eliminating the high input impedance and it also used for measuring the measurement and test equipment purpose. Instrumentational amplifier main applications, biomedical applications like ECGs, EEGs. Next, instrumentational amplifiers are used in earthquakes, temperature measurement devices, sensors, and we are also observed with some differences between instrumentational amplifier and op amp. So op amp is nothing but operational amplifier. It works as either inverter or integrator, differentiator or adder, subtractor, comparator. Instrumentational amplifier, it contains the 3 inputs. The 3 inputs mainly used for first measurement and test equipment. The main advantage of instrumentational amplifier is nothing but high CMRR. Why high CMRR need is nothing but high CMRR, it indicating the low noise. The output of noise will be low. So that is nothing but the output will be more accurate. So op amp, the best advantage of compared with op amp instrumentational amplifier is high accurate signal and high CMRR value. High CMRR indicating the low noise, whereas in op amp the CMRR value will be less. Normal op amp CMRR stands for common mode rejection ratio. So instrumentational amplifier, it is used to amplify only the inverting and non-inverting inputs, and it also eliminate both the common mode signals will be present in the inverting and non-inverting signal. So it will be amplify only inverting and non-inverting signal and it eliminates the common mode signals which is present in inverting and non-inverting terminal. That is nothing but it rejecting the common mode signal. So common mode rejection is nothing but it we can get the high accurate output. So this is the main advantages in instrumentational amplifier. These are already completed in previous classes. Today we are discussed about instrumentational amplifier using 3 op amp, 3 op amp block diagram and working function of instrumentational amplifier. In previous class just we can discuss about instrumentational amplifier definition, differences between instrumentational amplifier and some of applications related to instrumentational amplifier. First, now I am going to explain today's class instrumentational amplifier using 3 op amps. First, instrumentational amplifier is a special amplifier which is used for low level amplification. This is the main advantage along with high CMRR. It will be used to amplify the low level signal. So the instrumentational amplifier is used for low level amplification with high common mode rejection ratio. High common mode rejection ratio, it indicating the low noise and high accuracy. So the special amplifier, instrumentational amplifier is a special type of amplifier which is used for low level amplification, low signal amplification, and also it is suitable for high CMRR, high common mode rejection ratio, high input impedance to avoid loading effect, and the low, it uses low power consumption, and some features is called the instrumentational amplifier. It is a special type of amplifier which is used to amplify the low level signal and it is used for high CMRR purpose, and also it is used to eliminating the high input impedance, avoiding the high input impedance for loading effect purpose, and it uses only low power consumption. This is all about instrumentational amplifier. Such a special feature, instrumentational amplifier, have become integral part of modern testing and measurement instrumentation. The special feature of instrumentational amplifier where we can use is nothing but it is the integral part of modern testing and measurement instrumentation. So this is the block diagram of instrumentational amplifier. So the block diagram of instrumentational amplifier, it consists of, first, this is the block diagram. The block diagram, it consists of 3 op amps. One is the A1 op amp, second one is the A2 op amp, and A3 op amp. And it contains the resistors. The A1 op amp input is V2 and A2 op amp input is Vin. So A2 op amp will be connected with non-inverting input, and A1 op amp will be converting with inverting input. A2 op amp is nothing but inverting input. A1 will be connected with non-inverting input. Inverting input is indicated by the minus symbol, and non-inverting input is indicated by the positive symbol, that is nothing but plus. So A2 will be connected with inverting input, A1 will be connected with non-inverting non-inverting input, and V0 is the output. Here the V0 is the output, R2 is resistor, R1 resistor, R1 R dash, next R2 R2 dash. Working function of instrumentational amplifier. So the op amps A1, A2 are the voltage followers, or it can also called the buffer circuit. It acts as the input stages for the each of input is V1 and V2. So these are the two op amps, V1 and V2. A1 and A2. A1 and A2 are the two op amps. The two op amps, it consists of input voltages V1 and V2. So V1 voltage will be connected to A2 op amp inverting mode, and V2 voltage will be connected to A1 op amp non-inverting mode. So A1, A2 op amps, it can work as the voltage follower or buffer circuits, acting these input stages of V1 and V2. So the A1, A2 amplifiers are also called voltage followers or buffer amplifiers. Next, they have zero differential input voltage. Whenever the differential input voltage is 0, the output VID is also 0. That is nothing but VID. The voltage across differential inputs is 0. Under such condition, the common mode signal is 0. That is nothing but the differential input is equals to 0 means the common mode signal is 0. Whenever it will be possible is nothing but V1 is equals to V2. The voltage across the resistor are 0. The voltage across the resistor R is 0. Here the resistor R, voltage across the resistor. The voltage across the resistor is 0. When it will be 0 means V1 is equals to V2. When V1 is equals to V2 means the differential amplifier output V0 is equals to V1 minus V2. But V1 is equals to V2 means the differential output and differential amplifier output V0, it indicating the 0 volts when V1 is equals to V2. The differential input voltage VID is 0. Under such conditions, the common mode signal is also 0. That is nothing but V1 is equals to 0. The voltage across the resistor is also 0. The voltage at the inverting terminal of the buffer is equals to the input voltage. Next, since no current flows to the resistor R and R dash, the output voltages are V2 dash is equals to V2 and V1 dash is equals to V1 respectively. So when no current flows to the resistor R and R dash, this is the R, this is the R resistor, this is the R resistor, and it is a R dash resistor. Whenever no current flows to the R and R dash resistor, the output voltages are V2 dash is equals to V2 dash is equals to V2 and V1 dash is equals to V1. So whenever no current is nothing but whenever no current flows to the terminals R and R dash, it indicating the output voltages V2 is equals to V2. V1 dash is equals to V1. Next, If V1 not equals to V2, V1 is equals to V2 means the common mode signal is 0 and the differential gain signal is 0. For example, if the input voltage 5 volts, V1 is equals to 5 and V2 is equals to 5, the differential gain V0 is equals to V1 minus V2. Here V1 value, for example, V1 value is 5 volts and V2 value is 5 volts, then differential gain V0 is equals to V1 minus V2. That is nothing but 5 minus 5, it indicating the 0. The differential voltage is 0. The differential amplifier output V0 is equals to 0. That is nothing but both the inputs are same value or both the inputs are 0. When V1 is equals to V2 is equals to 0 also, the same problem will be arises. That is nothing but the differential gain is 0 only. The differential amplifier output is 0. Whenever V1 is equals to 0, that is nothing but first input is 0 and second input is 0. The differential output V0 is equals to V1 minus V2. That is nothing but 0 minus 0, it indicating 0 only. So in that case also differential input voltage 0 and the common mode signal 0. And second another case is nothing but both the inputs are same. When both the inputs are same also, the differential input voltage is 0 and common mode signal is 0. The 0 condition will be arises in only two cases. One, both the inputs are equal, that is nothing but V1 is equals to V2, or both the inputs are related to 0. If at all it will be 0, the output is 0. Next case, third case, one case is 0 inputs and second case is equal inputs, and the third case is V1 not equals to V2. However, if V1 not equals to V2, the current flows to the resistor. If V1 dash is equals to V2, V2 dash is equals to V2, V1 dash is equals to V1 is nothing but no current flows to the resistor. When the current flows to the resistor is nothing but that two voltages are not equal. V1 not equals to V2, then current flows to the resistor R and R dash. When V1 is equals to V2, no current flows to the R and R dash. When V1 not equals to V2, the current flows to the resistor R and R dash. Then that state V2 dash minus V1 dash is greater than V2 minus V1. V2 dash minus V1 dash is greater than V2 minus V1. When no current flows, V2 dash is equals to V2, V1 dash is equals to V1. When current flows, V2 dash minus V1 dash is greater than V2 minus V1. That is nothing but, therefore the circuit will have more differential gain and CMRR is compared to the more differential gain and more CMRR compared to single op-amp circuit. Next, the current flows to the resistor R dash is the R dash. When the current flows to the resistor R is equals to R is nothing but V is equals to IR. So R is equals to R is nothing but the resistor relation is nothing but it will be in terms of V is equals to IR. R is equals to I by V. Next, R is equals to I is equals to V1 minus V2 by R. Next, and the same current I will flow through the resistor R in the direction. The current flowing through the resistor R is current flowing resistor R is equals to R is in terms of I is equals to V1 minus V2 by R, and the same current I will be flow through the resistor R in the direction. Next, the voltage at the non-inverting terminal of op-amp A3 is nothing but the non-inverting terminal of op-amp A3. This is the A3. So, A3 we are connected with non-inverting terminal R2 and A2. Next, the voltage at the non-inverting terminal of op-amp A3 is the R2 V1 dash by R1 plus R2. By using superposition theorem. Superposition theorem is nothing but one input will be calculated and the other input will be represented as 0. Next, second input will be 0 and the first input is 0 and second input will be connected. It finally, we can add both the inputs. In two inputs, one will be connected to circuit and other will be connected to ground case. In case 2, one will be connected to input case and other will be connected to ground. Finally, we are adding. So, at the same time, the voltage at the non-inverting terminal of op-amp A3 is R2 V1 dash by R1 plus R2. By using superposition theorem, we can get the V0. V0 is the output voltage. The output voltage which is related to 3 op-amps. V0 is equals to, this is the output voltage V0. So, the V0 will be contains the values of R2, Next R1 R dash resistors also. So V0 is equals to R2 by R1 V2 dash plus 1 plus R2 by R1 into R2 V1 dash by R1 plus R2. So V0 is equals to R2 by R1 V dash of 2 plus 1 plus R2 by R1 R2 V1 dash by R1 plus R2. So simplifying the above equations, then we can get the V0 is equals to R2 by R1 into V1 dash minus V2 dash. Simplifying the above equation, the simplifying this equation, then we can get the V0 is equals to R2 by R1 into V1 dash minus V2 dash. Since no current entering in the op amp, the current value I is equals to V1 minus V2 by R, which flows through the resistor R. No current flowing to the op amp, but the current flowing through the resistor R. So I is equals to V1 minus V2 by R. Otherwise the I is equals to 0, but resistor has some current flows through this common, which flows to the resistor R. V1 dash is equals to R dash I plus V1. So here V1 dash is equals to R dash. In place of I, we can substitute V1 minus V2 by R. In place of I, we can substitute V1 minus V2 by R. So R dash I is nothing but V1 minus V2 by R. We can write as R into V1 minus V2 plus V1. Next, V2 dash is equals to minus R2 dash I plus V2. Next, here also say minus R2 dash is nothing but minus R dash. In place of I, we can write V1 minus V2 by R. So R dash by R into V1 minus V2 plus V2. Next, substituting both the values in the above equation. Both the values is nothing but V1 dash value and V2 dash value. V1 dash and V2 dash in equation 1. V1 dash is equals to R dash by R into V1 minus V2 plus V1. Second, V2 dash is equals to R dash by R into V1 minus V2 plus V2. So both are same, only in place of here V1, this is a V2. V2 dash is equals to the value with respect to in V2 terms. V1 dash is equals to value comes with V1 terms. Next, by substituting V1 and dash and V2 dash in the above equation, then we can get the V0. V0 is equals to R2 by R1 into 2R dash by R into V1 minus V2 plus V1 minus V2. That is nothing but V0 is equals to, V0 is the output voltage using 3 op amps instrumentational amplifier. So V0 is equals to R2 by R1 into 1 plus 2R dash by R into V1 minus V2. R2 by R1 into 1 plus 2R dash by R into V1 minus V2. By using variable resistor R, the gain of the instrumentational amplifier can be varied. Here R is the variable resistor. By varying by using a variable resistor R, the gain can be varied. Next, instrumentational amplifier using 3 op amps. So this is a 3 op amp instrumentational amplifier. OA1 stands for operational amplifier number 1, operational amplifier 2, and third one is the operational amplifier 3. Next, V1 is the input of operational amplifier 1. The input is connected to inverting terminal of operational amplifier 1. Next, OA2 is nothing but operational amplifier 2. The operational amplifier 2 is the input will be connected to non-inverting terminal V2. Here also non-inverting terminal V1, non-inverting terminal V2. Next, OA3 stands for operational amplifier 3. It contains R2 resistor. Next, R1, R2 will be connected to operational amplifier 3. V0 is the output voltage. V0 of dash and V0 of double dash is the outputs of operational amplifier 1 and operational amplifier 2. The V0 is the final output of circuit. Final output is nothing but instrumentational amplifier using 3 op amp circuit. First, this is the designing of instrumentational amplifier. First, instrumentational amplifier, it uses 3 op amps. The instrumentational amplifier, it uses the 3 op amp names as OA1, OA2 and OA3. OA stands for operational amplifier. So, operational amplifier 1, operational amplifier 1, operational amplifier 2 and operational amplifier 3. This is the three main instrumentational amplifiers. OA1, OA2 are referred as input or first stage. The OA1 and OA2 are the inputs or first stages, and OA3 it relates the output or second stage of circuit. So first stage contains the input values like OA1 and OA2, and second stage it contains the output, that is nothing but OA3. OA3 forms the output or second stage. OA1 and OA2 are connected to non-inverting mode, and OA3 it acts as a difference amplifier. Operational amplifier 1 and 2 are the connected in non-inverting terminal. Operational amplifier 1 and 2 are connected in non-inverting terminal, and the operational amplifier 3 is connected in a difference amplifier. Operational amplifier 3 will be connected in difference amplifier. The operational amplifier 3 contains the values of operational amplifier 1 and 2. So it contains the outputs of operational amplifier 1 and 2. Next, the drawback of difference amplifier using one op amp. The drawback of difference amplifier using one op amp is that unequal input impedance. The difference amplifier it contains the unequal input impedance. So this is overcome by connecting the OA1 OA2 to input of OA3. So why we can overcome is nothing but the OA1 is nothing but operational amplifier 1 and 2 it will be acts as a buffer amplifiers. The buffer amplifiers is used to eliminating the input impedance problems, unequal input impedance or high input impedance. It will be eliminating the input impedance problems. That's why we are using buffer type operational amplifiers. The buffer type operational amplifiers in eliminating high input impedance or input impedances, impedance matchings, high input impedance or impedance matchings. It eliminates the impedance matching problems first. Next, it contains high input impedance. The buffer amplifier contains high input impedance, and it also eliminates the impedance matching problems, and it will be mainly used for measuring and test equipment purpose. So the drawback of differential amplifier is a op amp. It uses unequal input impedance. So the unequal input impedance will be overcome by operational amplifier 1 and operational amplifier 2 to input of OA3. Next, the output value can be calculated as the operational amplifier output voltage can be calculated as first we are taking first amplifier. So the output voltage will be depends on two operational amplifiers, that is nothing but OA1 and OA2. First we are taking the op amp 1, operational amplifier 1. To find out output voltage operational 1, we are applying superposition theorem. This is the operational amplifier 1. So find out in the operational amplifier output is nothing but V0 of dash. Next, second operational amplifier is nothing but OA2. The output is V0 of double dash. So first find out in operational amplifier 1 value. First one is the consider V1 is acting alone. V1 is nothing but V1 is the non-inverting input of operational amplifier 1. OA1 non-inverting input of operational amplifier 1. So consider V1 is acting alone. That is nothing but Vx is equals to 1 plus R3 by Rg into V1. So Vx input volt, Vx is nothing but output of operational amplifier. So Vx is equals to 1 plus R3 by Rg. Where R3, this is R3. So R3 by Rg into 1. Rg is a gain resistance. Next, Rg into V1. Next, to consider V2 is acting alone. So V2 is nothing but second input. Second input will be connected to operational amplifier 2. That is nothing but Vy is equals to minus R3 into V2 by Rg. Minus 1 plus, this is the equation of non-inverting gain, 1 plus R2 by R1. This is the inverting gain is nothing but minus R2 by R1. That is nothing but R1, R2. So here we are writing is Rg, 1 plus R3 by Rg into V1 minus R3 by V2 into Rg. Next, V3 is equals to Vx plus Vy. Vx is nothing but 1 plus R3 into Rg, 1 plus R3 into Rg, V1 minus, plus of minus indicating minus only. Next, R3 into V2 by R3 into V2 by Rg. R3 into RG by VG. Next, RG. Next one. Similarly, for operational amplifier 2, we can write V4 is equals to 1 plus R3 RG V2 minus R3 V1 by RG. So the V3 and V4 are the acts as the input to OA3. So this is the V3 and V4. V3 and V4 it acts as the inputs to OA3. V3 is nothing but it will be comes from V3 comes from V1 and V4 comes from V2. So V3 and V1 can be connected to OA3 inputs. OA3 is nothing but operational amplifier 3. So therefore OA3 will have V3 and V4 acts as the inputs to OA3. For OA3 operational amplifier 3 also we have applying again superposition theorem. The output becomes V0 is equals to R2 into V4 minus V3 by R1. Next, that is nothing but R2 by R1 into 1 plus R3 by RG into V2 minus R3 V1 by RG plus minus of 1 plus R3 RG V1 plus R3 into V2 by RG. That is nothing but here we can substitute the values of V4 and V3. The V3 value is nothing but 1 plus R3 by RG into V1 minus R3 by V2 into RG. The V4 value indicating 1 plus R3 by RG into V2 minus R3 by V1 into RG. Both the values will be applying here. V0 is equals to R2 minus V4 minus V3 by R1. Then we can get this equation. Next, simplifying the above equation, then we can get R2 by R1 is equals to 1 plus 2R3 into 1 plus 2R3 by RG into V2 minus 1 plus 2R3 into RG V1. That is nothing but the V0 value. V0 is the output. V0 output of instrumentational amplifier is nothing but it will be related to R2 by R1 into 1 plus 2R3 by RG into V2 minus V1. By varying RG, we can adjust the gain of instrumentational amplifier. Next, instrumentational amplifier using 3 op amps. The most commonly it will be used, it consists of 3 op amps. The most commonly used instrumentational amplifier consists of 3 op amps. In this circuit, non-inverting amplifier is connected to each input of differential amplifier and it provides high input impedance for extract measurement and data from transducers. For extract measurement of input data from transducers, the main advantage of 3 instrumentational amplifier is the gain of 3 instrumentational amplifier circuit can be easily varied and controlled by adjusting value of R gain. So the gain value will be easily varied and controlled by R gain without changing the circuit structure. Next, the gain of amplifier depends on the only external resistors used. Hence, it is easy to set the gain accurately by choosing the resistor values carefully. So, the instrumentational amplifier advantages is nothing but the amplifier can be easily varied, control adjusting the gain without changing the circuit structure. So, it depends on only the gain, R gain. Resistor gain type of resistor, that is nothing but RG. Next, the gain of the resistor gain is depends on, or the gain of amplifier will be depends on the external resistors. So hence it is easy to control the gain and accurately by choosing proper resistor values. Next, advantages of 3 instrumentational amplifiers. Again, the 3 input impedance amplifier, the 3 input impedance of instrumentational amplifier is dependent on inverting and non-inverting amplifiers in the circuits in the input stage. The input impedance and the input impedance of non-inverting amplifier is very high, and the output impedance of instrumentational amplifier and the output impedance of difference amplifier is low. Input impedance is high, output impedance is low. The CMRR means the common mode rejection ratio of App amp 3 is nothing but app amp 3 is very high and almost common mode signal will be rejected. So app amp 3 is nothing but output operational amplifier. The output operational amplifier has the high CMRR value. High CMRR indicating it contains low noise and high accurated. That's why the CMRR of output amplifier 3 is very high and almost the common mode signals will be rejected. The common mode signals will be eliminated. This is also instrumentational amplifier, consists of 3 op amps. The 3 op amps names it indicating A1, A2, A3. A1 is the instrument op amp 1 followed with input voltage 1. Op amp 2 followed with input voltage V2. Next op amp A3. The op amp A3 has the outputs of the op amp A3 inputs is the A3 inputs is the output of A1 and output of A2. A1 and A2. And the output value V0. The V0 is equals to minus R4 by R3 into 1 plus 2R2 by R1. This is the formula of our gain of instrumentational amplifier. The gain of instrumentational amplifier is nothing but minus R4 by R3 into minus R4 by R3 into 1 plus 2R2 by R1. So, here for one resistor gain adjustment set R4 is equals to R2 and fixed R2. R2 will be fixed and R4 is equals to R3 gain adjustment purpose. Next, the instrumentational amplifiers has very high input impedance and it can optimize CMRR, means it have high CMRR, low noise. Next, the gain can be set with one resistor. Here the gain can be set with only one resistor. So the gain adjustment is using of R4 is equals to R3. Next R2 will be fixed resistor. This is all about instrumentational amplifier using 3 op amps. There are some multiple choice questions related to this. An instrumentational amplifier or instrumentation system does not include transducer, instrumentational amplifier, automatic process control, or tester. Last one is the D option is tester. The answer is tester. An instrumentation system does not include tester. Why we can tell tester is nothing but except tester, the remaining blocks from the input, intermediate and output stages of instrumentation amplifier. Except tester, the remaining blocks from the input, transducer input, instrumentation amplifier, automatic process controller is the output stage. So these are the main blocks and the tester is not used in instrumentational amplifier. Next, general purpose op amps used in applications as the op amps used in applications as instrumentational amplifier, differential instrumentational amplifier, inverting instrumentational amplifier and non-inverting instrumentational amplifier. So the general purpose op amps used in applications is that first one is answer is the differential instrumentational amplifier. Why we can choose answer differential instrumentation amplifier is nothing but when requirement for the application are not too strict, the general purpose op amp can be employed with a differential mode. The requirement is not strict, so then we go for general purposely differential amplifier. So the general purpose op amp can be employed in a differential mode and such amplifiers are called differential instrumentation amplifiers. Next, third question. Characteristics of non-inverting amplifier is identical to. So the op amp it consists or it working on two modes. One is the inverting mode and second one is the non-inverting mode. That is nothing but op amp consists of two inputs, inverting input and non-inverting input. So the characteristics of non-inverting amplifier is differential amplifier with 1 op amp, differential amplifier with 2 op amp, differential amplifier with 3 op amp and none of the above mentioned. So the characteristics of answer is nothing but differential amplifier with 2 op amps. Characteristics of non-inverting it consists of differential amplifier with 2 op amps. That is nothing but the characteristics of non-inverting terminal are identical to differential amplifier with 2 op amps and the gain of amplifier is same. That is nothing but non-inverting gain is nothing but 1 plus general purpose non-inverting gain is nothing but A is equals to 1 plus RF by R1. So it is consist of RF is the feedbacking resistor and R1 is the input resistance. That's why the characteristics of non-inverting amplifier will be identical to differential amplifier with 2 op amp gain. The 2 op amp gain and the amplifier are the same. Next, fourth question. How it is possible to vary the voltage from closed loop gain to the open loop gain? So how is it possible to vary? how is it possible to vary voltage from closed loop gain to open loop gain? How it can vary from closed to open? By using differential amplifier with larger gain, or by using differential amplifier with small gain, or by using differential amplifier with variable gain, or by using differential amplifier with differential gain. So we can possible to vary voltage from closed loop gain to open loop gain only the condition of differential amplifier with variable gain. So then only we can vary the voltage from closed loop to open loop by using differential amplifier with a variable gain. That is nothing but the variable gain in a differential amplifier. It can be obtained by using a potentiometer. The potentiometer is used for varying purpose. So the variable gain in a differential amplifier can be obtained by using a potentiometer. So depending upon the position of upper and the potentiometer, voltage gain can be varied from the closed loop gain to open loop gain. So by using differential amplifier, so the differential amplifier can be obtained from potentiometer. So that's why we can vary. That's why the answer is by using differential amplifier with variable gain. The variable gain from the potentiometer. So depending upon the position of potentiometer, voltage can vary from closed loop gain to open loop gain. Next, last question is, when does the op-amp set to be operate in a common mode configuration? So the op-amp set to, when we can tell the op-amp work is in common mode configuration. That is nothing but when the two input voltages are equal is the A option. B is nothing but when the two input voltages are equal to the output voltage. When next C is the when the same voltage is applied to both input terminal of op-amp. And the last one is the when different input voltages is applied to both input terminal of op-amp. So op-amp is said to be work on common mode rejection ratio is nothing but the answer is when we are applying same voltage is applied to both input terminals of op-amp. That is nothing but when the same input is applied to both input terminals of op-amp, the op-amp is said to be running on the common mode configuration. So it is possible only the applying same inputs. That is nothing but applying common inputs. These are the some multiple choice questions are related to instrumentational amplifier and CMRR. So today we are completed about first instrumentational amplifier. It is a low level amplifier used for high CMRR, and it also amplify low level signals. It have low noise, high accuracy. Next, it contains 3 op-amps. The 2 op-amps output will be connected to third op-amp. Next, here first condition, no input is applied or the input is equals to 0. That is nothing but no current flows to the circuit. When the inputs are different, then we can find out the output voltage V0. The output voltage V0 depends on the two inputs. The two inputs is nothing but the 2 op-amps which is related to op-amp 1 and op-amp 2. The output voltage will be the values of, contains the values of R2, R1, 2 input resistors and 1 plus R2 dash by 1 plus 2R dash by R into V1 minus V2. This is the instrumentational amplifier using 3 op-amps. The 3 op-amps is OA1, OA2, OA3 is nothing but operational amplifier 1, 2, 3. One will next 1 and 2 are connected non-inverting mode and 3 is connected as a differential mode. That is nothing but for the operational amplifier to work as a difference mode. And then we can calculate the ones V1 is by using superposition theorem. We can calculate the values. First, V1 is acting alone. V1 is the input of operational amplifier 1. V2 is operational amplifier 2. Next, the outputs will be V3 and V4. So once V1 alone, when second time V2 is alone, and third V3 and V4 alone to input of OA3. Then we can find out the V3 is nothing but Vx plus Vy. Vx consists of output of V1 and Vy is nothing but output of Va2. Next, V4 is nothing but OA2. OA2 is nothing but V4. V4 can also 1 plus R3 into Rg by Rg V2 minus R3 by V1 Rg. Then we can substitute the equation And finally we are getting the output value V0 is equals to R2 by R1 into 1 plus 2 R3 by Rg V2 minus V1. Instrumentational amplifiers used in non-inverting configuration. It input to the differential amplifier. Next it extract data from transducers. The instrumentational amplifier will be adjusted due to gain of resistor, means it can be depends on gain resistor value. Next then only we can find out the external accurate value. It depends on the external resistor, hence we are easy to find the gain. Next, the input impedance is very high. Here we are using buffer amplifiers, and op amp O3 is very high, and almost the CMRR of op amp 3 means common mode rejection ratio of op amp 3 is high, and almost all the common signals will be rejected. Next, the instrumentational amplifier does not contain tester. It contains transducer, instrumentational amplifier, and it contains automatic process controller like operational amplifier 3. Next, general purpose op amp, it work as a differential instrumentation amplifier. The differential instrumentation amplifier is nothing but just the requirement is not strict, not too strict. The purpose can be employed with differential mode only. Next, the non-inverting characteristics is nothing but it contains two inputs. Differential amplifier with two inputs, that is nothing but gain A is equals to 1 plus RF by R1. RF and feedbacking resistor, R1 is the input resistance. How is possible to vary the voltage, closed loop voltage, vary the voltage from closed loop to open loop, means by using differential amplifier variable gain. By using variable gain we can possible to vary the voltage from closed loop feedbacking to open loop gain. Next, how does the CMRR op amp set to be in common mode configuration is nothing but when we are applying same voltages, so it will be work on common mode configuration or at common mode inputs. These are the today's topics: instrumentational amplifier using 3 op amps, definition, circuit diagram, working. Next, 3 op amps along with the instrumentational amplifier, applications, advantages. Next, some multiple choice questions. In next classes we can discuss about types of ADCs and DACs. ADC stands for analog to digital converter, and DACs is nothing but digital to analog converter. We can discuss the topics in next sessions. Thank you all.